Hello, everyone. We're just going to wait for 2 more minutes or 3 more minutes to get more students joining. All right, let's start with neural networks. We are in part 2, so let me share the slides with you. I also just want to let you know that I recently updated the slides, so you can, go to Canvas and get the updated ones for part 2 of neural networks. Okay, so it's recently updated. I updated this this morning. Updated the slides, and I also you can also find the R code for a neural network as well. This was posted last week. So if we will have time by the end of the class today, we will look at the code and see how we can use neural network in R. Okay, so let's start. Just want to make sure that I'm recording. Okay. So before, let me see if anybody has any questions on chat. This is homework 9 is the last homework. There will be no more homework, no more assignments after this. So even though we will have one chapter left, one topic left, that's unsupervised learning, we will finish this next time. So today we will finish all neural networks. And the homework 9 is about neural networks. Next class, we will have our unsupervised learning class. There will be no assignments assigned afterwards. And so you will have enough time to finish and finalize your project. So the week after next week, we will start project presentations. For speaking of the postponing, homework 9 has already been postponed till April 10. Okay, so if you look at the due date for homework 9, it was supposed to be April 8, so I pushed it 2 days till April 10. For the extra credit, I will let you know, maybe. I will let you know, Nipur, for the bonus assignment. I'll send an email if we are planning to postpone the due date for it. And we will, we'll talk about it. We'll send an email. Let me talk to Riamal about it, and we will see when, till when we can postpone the due date for that. All right, I'll consider it. Okay, so neural networks. One more question. Okay. So neural network is one of the the most powerful algorithms in machine learning nowadays. And we started talking about it last time. We didn't finish, so hopefully today we will finish everything that is you need to know about neural networks. And still, this is basically a brief introduction to neural network. In a way to understand the basic standard type. So we know that we have 3 main types in neural network. We have the standard neural network, the so-called feed-forward neural network. That's the kind that a lot of people are still using nowadays in structured data. The same way we used, regression methods, tree-based methods, SVM on structured data for classification or regression problems. So we're still using the standard type of neural networks for this, similar problems. The other kinds of neural network, including recurrent neural network and convolutional neural network, are mostly used with unstructured data for image analysis, for video and audio and text analysis. Maybe in another course you will learn about these kinds of neural networks and deep learning in general. So, to continue with our standard neural network representation, so we started with the model representation, and we will choose an activation function that we are all familiar with to make it easy to understand what's going on inside the neural network. The activation function of our choice is going to be a sigmoid function, a logistic function that will have the same behavior as logistic regression, except that the neural network is pretty much multiple units. So instead of just one logistic regression function or one logistic unit, we have multiple logistic units. So keep in mind the function that we're using in those neurons inside these nodes or these units is the logistic function. So in this representation in here, I will start to have a mathematical representation that we will be using today in today's class to walk you through pretty much the process inside the neural network and the kind of calculations or the steps of the calculations in the forward phase and the backward phase by which the neural network is learning from the examples or the samples that you have in your training data set, and by which the weight or the parameters of the model will change to give us an accurate prediction for the problem. Okay, so let's start with what we have here. So this is as you can see in here, we have a simple neural network. We have our input layer. We have three features: x1, x2, and x3. We have one hidden layer and one output layer. And the terminology in here that we're using, so we're using h theta of x. This is going to be our hypothesis. That's like the function that we're trying to model, or the function that we're trying to figure out, that will give us the prediction. The values that we will calculate inside the nodes, inside each node, and again, you can think of each node in here as a way by which we're transforming, or we're mapping from one input to an output. And this mapping is pretty much controlled by the weights that we assign to the links. Okay, and also remember that in drawing a neural network, we don't draw the what we call them the bias units. So the bias units are needed to estimate parameters for our model. So we have a bias unit x0 that is equal to 1. That is also fully connected to the others. And the same thing in here, we have a bias unit that is also connected. That's A0, sorry, 1. Okay, so we don't draw the bias units in the representation of neural network, but keep in mind that those are there all the time. Okay, so inside the nodes or the neurons, we have the terminology again. We call the values that we will calculate activations. And for the notation that we're using in here, this superscript between parentheses, that's the layer number. And the subscript in here is the unit number. So this is A layer 2, that's the first unit activation, A1 at layer 2, A2 layer 2, still the same layer. So we have A1, A2, and A3. And for the one at the end in here, we can also call this an activation, the same thing. So this is going to be A1. We only have 1, but the layer in here will be 3. So we can basically say this value in here is an activation, and the layer number will be number 3. Just, oh, I'm sorry. One more time, share. All right. Okay, so so the case in here, we have pretty much the layer 1, the input layer, one hidden layer, one output layer. We have activations. So this is, the whole thing is A2, and you can think of it as a vector of 3 values. And we have in here our A3, it's just a vector of 1 value because we only have 1 unit. Okay, and remember that we have thetas. Thetas are the parameters or the weights. We can call them. You can either call them in the terminology of neural network, either weights or parameters. And we will use the theta as our notation in here for to represent those variables, those parameters. So the set of parameters between the input layer and the hidden layer, this is going to be our theta 1. So theta 1 in here will be a matrix, of weights controlling the mapping from layer 1 to layer 2. And theta 2 will be another matrix in here that controls the mapping from the layer 2 to layer 3. How many thetas or how many weights we have in theta 1. So basically, and again, remember always, let me just keep the drawing for the bias unit. That's x0, which is equal to 1. Just keep it in here to kind of calculate how many, to determine how many thetas we have. Okay, so for theta 1, look at how many units we have. We have 4 units, and all those 4 units are fully connected to 3 units. So you have 3 times 4. Okay, so 3 times 4, 12 parameters that we have in our theta 1. So the dimension of the matrix theta 1, we basically put it in a matrix notation. So theta 1 in here is a matrix of size 4 by 3. Okay, so I'm sorry, 3 by 4. Okay, so it's a 3 by 4. So 3 will be the destination. Think of it this way. So the 3 will be the how many nodes in the second layer. So we have 3, and how many nodes in the first layer? We have 4. Remember that we have the bias unit. So always keep in mind that there is a bias unit in here. So the matrix dimension will be 3 by 4. Okay, so it's in reverse, right? So it's not 4 by 3, it's 3 by 4, pretty much. And for theta 2 will be 1 by 4. Okay, so it's only one row of 4 elements. And remember, in here we have A0 equal to 1 as the bias unit in here, and that's connected. So you have 1, 2, 3, 4 values or 4 thetas that you need to estimate in here, by which you will control the mapping between the hidden layer and the output layer. So the parameters in here in theta are the most important part in determining the hypothesis function in here that will estimate or predict, okay, our outcome. Training a neural network is all about finding or optimizing or updating the weights in here, because initially those weights will be randomly initialized, and then we go through phases of introducing or feeding the training samples into the neural network, by which we iteratively update the weights to have a cost of 0. Or as close as 0, where we correctly predict or we correctly classify on the training data. Okay. So, if we will look at the calculations inside each node, so if we will, if I will take, for example, this unit in here, and I will look, if we will look at A2, the activation, how do we determine the value inside this node? So it's 2 steps. Remember, we have 2 steps happening inside each node. The first step is a weighted sum of the input. So you take the input features that you have, including the bias unit, which is equal to 1, and you multiply this by each input by the weight. So for this unit in here, if we look at, choose a different color. So for this specific unit in here, we have a line or a link that is coming from this unit, and also from x1, from x2, and from x3. And there is theta, and we will, have the subscripts for those soon. So you multiply each incoming, each feature in here by theta, that's the weight in here, and that's how we calculate the weighted sum. And after that, we apply the activation function. And the activation function in here, we are going to assume that we're using a logistic function, sigmoid activation function to do the mapping for us. Okay. So the question in here from Tara, the bias unit in the second layer. So we have a bias unit in here. So what do you mean 4 by 4? So this is for theta 1. Theta 1, you have how many we have. So okay, so for theta 1, how many thetas or how many weights inside this matrix? It will be 3 outgoing links connected to the three nodes in the hidden layer. So you have a total of 12 values, 12 weights in this mapping between layer 1 and layer 2. Now the way we lay out this matrix as a 3 by 4 is basically, if I will put this in a matrix notation, hold on just a second. So we have, in this case, 3 rows. Okay, so this is a 3 by 4. So we have in here 1, 2, 3, and we have 0, 1, 2, 3. Okay, so the first one in here is going to be theta 1, 0, and this is going to be theta 1, 1, theta 1, 2. This is theta 1, 3. Hold on just a second. Theta 1, 3. And the same thing in here, we have theta 2, 0, theta 2, 1, theta 2, 2, and theta 2, 3, and so on. So this is our matrix for theta 1. That's theta at layer 1. And this is, pretty much corresponds to, if I will put it in here. So this is theta 1, 0. This is theta 2, 0, and this is theta 3, 0. Okay. Now, if I will jump to x2 in here, so this is going to be, or let's continue with the other one from x1. So this is going to be theta 1, 1. This is going to be theta 2, 1, and so on. Okay. So it's pretty much like, to organize or to differentiate, right, between, so we need those subscripts to differentiate between the different parameters that we have to understand, those thetas belong to what node in the previous layer and connected to what node in the second layer. All right, let me take. Okay, so to understand the calculation that it's happening inside one node, remember that we have a summation and then we have an application of the activation function. So the next slide in here, in a way, shows the equation that we have for calculating the activations. So this is for A1, 2. So to calculate the value inside this node in here, we will take a weighted sum And remember also, to include the bias unit x0 in the calculation. So the theta in here, there is a sign to the link connecting to A1 to this node in here. Sorry, will be theta 10 times x0 plus the same thing. Go with pretty much all the links that goes into this node. So we have, and including of course x0. Okay, so I'm going to be choosing different colors. So this is theta 10, this is theta 11, this is theta 12, this is theta 13. Okay, so that's what's happening in here. We accumulate. So this is the weighted sum of the input features by their weights or their parameters, and then you use the activation function. And G in here is the choice in here again sigmoid. So our G of x will equal, and I'm going to use a different term than x. I'm going to use z. Okay, so I'm going to introduce a third, a different variable in here, z, to be this weighted sum, and g of z is going to be 1 over 1 minus e to the power minus z. So this is a sigmoid function that we will be choosing to give us the S-shaped behavior that we are all familiar with from logistic regression, and that's going to be our nonlinear mapping from input to output, but in this case in here from input to the activation in here. Okay, so we're not going all the way to output yet. So we do the same thing for for the all the units inside this layer 2. We calculate the activations, and then after that the activation at the unit in the output layer will be in the same way. We accumulate. We calculate the weighted sum. And again, this can be referred to as z. So this is z1 at layer 1, and there's going to be z1 at layer 2. And then we apply the g function in here, a sigmoid, to calculate A13, which is going to be, of course, the output of our hypothesis function. So this is A3, and that's it. Okay, that's the end. So this is pretty much how we do the forward phase, actually. So this is how we calculate from input to output. And the choice of the activation function in here is we have other options to choose from, but we will stick with this one to understand the learning in neural network, and because it's something we're familiar with. Okay. So this is again, rewriting using the z's in here. So we, the z value, each z value is pretty much the weighted sum, and this is so, and the a value is the activation after applying the function g. So back to the pretty much when we talked about theta, how many as a matrix in here again, the dimension of this matrix will be how many units in the layer j plus 1. Okay, so the dimension of j, theta of j, will be how many in j plus 1 times how many in the previous one, j, and then you add the bias unit. Okay, so when we talked about theta 1, that's the matrix that controls the mapping between layer 1 and layer 2, the dimension will be 3 by 4. Okay, so 3 is how many in layer 2, and 4 is how many in layer 1 plus the bias unit. In theta 2, it's going to be 1 times 4. So 1 is how many in the last layer, which is just 1 unit, and how many unit in the previous layer? We have 3, and remember we have always a bias unit that we don't draw with our neural network drawing. It's given that it's there, and of course we need those bias units pretty much to, and we set those to 1 because we need the theta associated. We need this extra parameter that we need to estimate, and this extra parameter is something that is similar to what we've seen in the logistic regression. It will be corresponds to the intercept, so it will be corresponds to beta 0. So, so the formulation of a problem in here requires us to add those bias units and set them to 1 because we need this. And I mean, I can't say it's additional. It's part of the model. It's not an additional parameter or additional weight. It's part of the whole equation. And it's required in here. So we need this. Okay, so this is pretty much a mathematical representation of the model, and in a way we understand now how the forward phase is done. Pretty much the process by which you calculate from input features to intermediate features to maybe another level of intermediate features, all the way to the end where you have your outcome. And the outcome will be like a prediction, right? It will be treated as a prediction. So, in a way, in here, if you think of just logistic regression and compare it with a neural network, in logistic regression, it's just 1 unit, but then again, neural network is multiple units. So when you have those in multiple layers, so what's happening in here is those activations now will become a new features that we learned from previous features. So if we will consider just 1 unit in here, you have your input features and you have weights assigned or associated with each one, including the bias unit. And if we're done with this is going to be just like logistic regression, exactly like logistic regression. But then again, we're using the value that we calculated in here, along with the other values that we calculated in the other units, as input that we will feed to another logistic regression unit in here. And this logistic regression is going to produce an output. So now our activations calculated in this layer will serve as new features that we will feed to the activate the nodes in the layers ahead. So this is pretty much what gives neural network this powerful ability to come up with very nonlinear hypotheses in many problems, and to be as one of the most successful machine learning methods is pretty much the learning of the complex features from or in pretty much in each layer. So what we have in here, for example, is from the input layer, we learn some features in this hidden layer, and then those features will be fed into the second layer in this. So this is layer 1 input, this is 2 and 3, and this is 4. So 2, 3 are our hidden layers. So more of the complex features that we learned in this layer in here will be fed into this layer, and now we have more complex features in this layer that we will feed into the last layer, where we will make pretty much the final decision in making a prediction, whether it's a classification or a regression. Okay. In a way, so this is what gives neural network its powerful, or what makes neural network very powerful. At the same time, this is what makes neural network considered a black box, is pretty much the inability to determine feature importance or to trace, the decision in here. How do we trace this back? So if you have a predicted value or a predicted class, how do we determine how much contribution each feature, or what is the contribution of each feature to this decision? Okay. Now, things will be easy if we are using only one one unit. If our model is just a simple single perceptron neuron, right? So just a single layer, and this is just where the logistic regression is done. So it's pretty much going to be like the same as applying logistic regression. And after, we have our function, will, make a classification in here. We can pretty much go back and look at the weights assigned or calculated or estimated for each input, x1, x2, and x3. And maybe from the weights in here, we can pretty much, say the feature importance in here is as, those are determined by the value estimated for those weights. So the higher the weight in here, it means this is an important signal coming from this input feature, and this input feature is more important than, for example, this one, if the value that we estimated in here is less than, and so on and so forth. So we can, treat this the same way we treated other methods, where the value of the coefficients that we estimated will determine the importance of the variables. So this is going to be easy if we only have like a single perceptron, a single layer perceptron, and that's it. But in reality, when we usually use neural network, we use a multi-layer perceptron, and it will be difficult in here to go and trace things back. So even if you have like a high weight on this link in here, so this high weight, and go back to the activations that causes this weight, maybe this is the highest one, and this highest one is coming maybe from many features, not just one feature. So maybe all those contributing the same to determining this activation value, and this activation value in here will be the one that mostly contributing to this one. But then again, it will be difficult to just kind of make a decision about the feature importance by going through those activation values that we calculated internally. So it's one way, yes, it's kind of, some people made it possible to determine the feature importance by going through those weights that we calculated. But when you have a very deep neural network, a very complex one, it will be difficult to determine for sure. Okay. Now, so we use neural network for classification and regression. For regression, we only need one output unit, and this output unit where we will calculate a value. For classification, if it's a binary classification, we need one output unit. But if it's a multi-class classification, we need k output units. So in this figure in here, we have 1, 2, 3, 4. So in layer 4, we have 4 units. So it means that we are making a 4-class classification. And in your encoding of the outcome, so maybe the y, your y in here is a class number, maybe class 1, 2, 3, or 4, or or a name of a class. Okay, so in your encoding, you need to encode this as using one-hot encoding. So your y now will be for the first class will be this notation in here, for the second class, for the third one, and the fourth one. Okay, so this is what we call one-hot encoding. So you need to encode y this way for the neural network to work for us in multi-class classification. And what's happening in here is basically a one versus all. Okay, so that's why we needed this much output unit. So in other words, you are creating 1, 2, 3, 4 classification. So and at the end, each unit will produce an output, a value between 0 and 1. And if the output in here, it doesn't have to be exactly 0 or 1, it's just a value between 0 and 1. So you may have an output in here coming from this unit, where you have a value of 0. For example, 8, and here maybe 0.1, 0.001, and this is maybe 0.009, maybe. Okay, so so the case in here, this is the largest one. So your prediction will be to this class where you have 1 0 0 0. So that's your prediction will be to the first class. So again, this is the notation that we use for the training set. And so we use, so the superscript in here is the sample number. Okay, so you have x1, y1, x2, y2 to x and ym, where y is one of those. Okay, so the y in here will be a one-hot encoding for the neural network architecture that you will be implementing, where you will have 4 output units. Okay. So just to remember, in multi-class classification in neural network, we do it using the one versus all, and you will have as many output units as the number of classes in your problem. So here's a quiz question for all of you, and the question in here is, if you have a multi-class classification problem with 10 classes, so now we know that the output layer will have 10 units. You have an input layer, one hidden layer with 5 units, and of course we will be using by default the one versus all. How many elements in theta 2? And again, theta 2 in here, the matrix of weights that will control the mapping between layer 2, the hidden layer, and layer 3. So we have 1, 2, 3, 4, 5 units in layer 2. This is L equal 2. And we have 1, 2, 3, so 1, 2, 3, 10 output units. And remember, it's all fully connected. Sorry. So we have fully connected neural network, and so on. So how many in between theta 2 as a matrix in here, how many values, right? How many elements inside theta 2? If you know the answer, you can send it in chat. 60 tera, that's correct. Okay, so in this case in here, you have 5 units, and then you have 10. So yes, 5 by 10 is 50, but then don't forget that you have a bias unit. Okay, so that's the case where this bias unit is 1, and of course this bias unit is also fully connected to the output layer. Okay, so this node in here will add to your 50 10 more, by which the number of elements will be 60. Okay, so 60 is the correct answer. Now, what is the dimension of the matrix theta 2? So theta 2 will be, so you have 10 times 6. Okay. All right, very good. Now, how do we actually, you can, that's a good question. Actually, you can choose your output to be 2, and if you have a binary classification, you can choose to leave it just 1, to just have a 1 output unit. or you can choose two, and you make a one-hot encoding of the two classes that you have. Okay. So, which in some problems where based on my experience, where it didn't matter if you choose one output unit for your binary classification, and then the value will be treated, of course, as a probability value between 0 and 1. I didn't see any difference than, for example, using two output units rather than one for binary classification. So it's the same. All right. So for training the neural network, it's all about modifying the weights and the parameter, and to go through the phases in here, the forward propagation, which is the forward phase, and then the backward phase, the back propagation, by which we can modify the weights iteratively. Okay, so the back propagation, although there's the terminology in here, so the back propagation algorithm, just in here to, I don't want you to be confused by the terminology. So the back propagation algorithm is the most common, most commonly used algorithm for neural network training. So this algorithm has two phases: the forward phase and the backward phase. And the backward phase is what we call back propagation. Okay, but still, like the whole thing, the two things are the back propagation algorithm. Okay, so the back propagation algorithm is not just just one phase; it's two phases. So now we know how the activations are propagated from the input to the output. I mean, we've seen in the previous slides how we calculate the activations. Just a weighted sum, and then you apply the activation function, and you move to the next layer, and you do the same thing, to the output, all the way to the output layer. Now, the backward phase, or the back propagation, is pretty much for the errors now. So we need to calculate the errors from the output layer, the last layer, and propagate those errors to the internal layers in between, all the way to the second layer. Of course, there is no errors associated with the input. Okay? Now, the calculating the errors in here is needed to modify the weights. And we're doing this, like we're going with the forward phase and backward phase to accumulate those error terms that we will be later on use in a gradient descent or any optimization algorithm to modify those parameters to minimize the cost. Okay. Now we will talk about the cost function. What's the cost function for our neural network, and how gradient descent work. So that's pretty much by the end today. We'll talk about it. What's this algorithm, and why do we need it? But first, let's see the two phases in here. We know the forward one, so that's easy. But let's look at the back propagation in here. So again, the forward propagation, we know how to carry this out. We know how to calculate the activations at layer 2, activations then at layer 3, and activations at layer 4, which is the output layer. And here we're assuming we have a 4-class classification, so we have 4 output units, and we can pretty much say that the activation at layer 1 will be your input. Okay, so that's what we have in here. So A1 is basically X, your input. Then you calculate the weighted sum of your input that you have, the thetas and your input, and then you apply the G function to get the activations at layer 2, then activations layer 3, the same thing. So we're familiar. Any questions about the forward propagation? So we fully understand how we propagate from input to activations to all the way till the end. All right. Now, the back propagation, that's a very long question. So why can't we get away with one less output for K classes like in categorical data analysis? This is just sort of how we visualize things, but we can just assume that if something doesn't land in. So the number of, if you're talking about the number of output units in neural network, we use one versus all. So each one in here, think of each one as a one classification on its own. Okay. So instead of like, you know, if you think of applying a classification method, so each node in here is a classification on its own by which it will produce an output that you will compare with the three other ones. So you need a total of K classification methods for K classes. Now, for the back propagation, that's where we propagate from all the way from the last layer to inward now, okay, in the other direction. And what we propagate in here is what we propagate are the errors. Now the errors, you know, that we will calculate at the output layer, that's kind of the easiest thing to do. We have our true outcome Y. Okay, so we have so we will use the delta letters in here as to represent the errors. So so we will use delta. L is the layer number, and J in here is the node number. And we will we need to associate, or we need to calculate the delta in here in each node. Think about it. Pretty much, since we have activation in each node, and also we have an error. This node is calculating, this node is producing. So we need to calculate those deltas for each node in each layer. And we'll start off with the delta in here at layer 4. So we'll have 4 deltas, 4 error terms in each node. And from there, from delta 4, we propagate to calculate delta at 3 and then delta at 2. Okay, so that's the propagation of the errors in here. Now, the delta 4 in here at node 1, 2, and 3, and 4, so we'll have 4 errors. So that's kind of the easy part, because you have your Y, you have your true outcome in here, and we pretty much subtract the activations that we calculated at layer 4 from the true outcome in here, and that's going to be our errors that we have. So, because the activation at layer 4 is the output of our hypothesis function. So our output of the hypothesis function here is like the predicted value or the predicted class. So you take the predicted class or the predicted value minus the true value or the true outcome, and that's going to be the errors that we have at the output layer. Okay. Now from the error terms that we calculate at each node in here, we go backward and we calculate the errors in the previous one. So for theta 3 in here, pretty much, if we ignore, just for now, guys, ignore these terms, okay? Ignore those for now. We will go back to them, okay? The errors at the layers in between will be pretty much calculated the same way we do calculate the activation, but this is going to be done in reverse. So we know that we have theta. So we have theta 1, we have theta 2, and we have theta 3. Well, let me use the parentheses. That's a layer number. So, pretty much the deltas in here that at the third layer will be calculated using the deltas that we calculate in this layer multiplied by the thetas. So you do things in reverse. So, if you think of what's the delta in this node in here, it will be the deltas. You see, this is, remember the links, okay? And each link will have a theta value assigned to it, and you have the deltas in each node. So you take the delta that you calculate for this node, multiply by this weight, plus this delta in here, multiplied by this weight. The same thing goes for the other ones. You accumulate everything in here. So this is how we calculate the deltas, by going with the thetas multiplied by the deltas that we already calculated in the previous layer, and so on and so forth. So the same thing for the delta at layer 2. You have your deltas that you calculated in layer 3, and you have your theta values in here, and you calculate it as a weighted sum, and now you have the error terms in the second layer. And we don't have, of course, error terms with layer 1, because layer 1 is the input, x. Okay, so the other thing in here that I want you to ignore for now, but we will come back to it, is this is a notation that we use for a derivative. So this is the derivative of the function, our g function. Again, we're assuming the use of a sigmoid function. So we take the derivative of the sigmoid function at z3. Okay, and this in here is dot star. That's an element-wise multiplication. So if you have one vector with values element-wise, another vector with values, so you just take this one multiplied by this one multiplied by this one to come up with another vector. Okay, so that's an element-wise multiplication. So let's ignore this for now, just to simplify it, to simplify the problem for us. And later on we'll come back to this. So the back propagation is simply, think of it as simple as multiplying the theta at the current layer with the error terms calculated from the layer ahead. Okay. We don't have delta 1. We don't have errors associated with the input. You don't change the input values x. Okay. Now, we need those delta values, and again, we will be doing this with each training sample. With each, so for each training sample in all of your training data, you go and do forward phase and calculate all the activations, and then for this one, again, sample, you calculate the error terms and all the layers all the way. So this needs to be repeated for all the training data samples that we have. And at the end, we will, apply gradient descent once we have accumulated all those errors for all of the training data. We apply gradient descent to update the weights. Okay, so we will, we will talk about it in detail soon, of course. Okay, so pretty much in a way to have this represented inside, now I believe you're familiar with what's going on with the forward phase and the backward phase, but let me just use one example in here, like really quick. Just a second. All right. So So what do we have in here? We will be calculating for the forward propagation. We will calculate first Z1, this is layer 2, to get us a 1 at layer 2. This is Z2, 2, to then get us a 2 after, of course, you apply the activation function. And, you know, in here the same thing. This is Z1, 3. This is Z1, Z2, 3 to get us A1 at 3. Okay, and same thing in here. You calculate Z1, 4 to get you A1, 4, and that's going to be, of course, your output output of the hypothesis. Now, for example, if I will just focus on one, if I will just focus on this one in here, so the Z basically is an accumulation of, or a weighted sum of theta 1, 0 at layer 2. So this link in here, and this is theta 1, 1, and this is theta 1, 2 at layer, they are all at layer 2. Okay, so pretty much Z1 will be equal, layer 3 will be equal to theta 1, 0 multiplied by 1. Okay, so that's the bias unit plus theta 1, 1. This is 1. Okay, but multiplied by A1 plus theta 1, 2 multiplied by A2, of course, at layer 2, and don't forget also the layers in here, to just be consistent with the notation that we're using. And once you have calculated Z, A will be, again, this is A1, 3, will be the activation function of Z. Okay, and the G in here is basically the sigmoid, so 1 over 1 minus A to the power minus Z. Okay, 1, 3. Okay, so that's the forward propagation, where we know how to do that. Backward propagation, so we calculate the errors. Okay, so we have the errors at layer 4, errors at layer 3 and 2. And let me just select one, as an example, because what's happening inside is pretty much very similar to all, right? So, remember in here the errors at the last layer is just, you need to subtract, yi minus A at layer 4. Okay, so that's pretty much how you calculate for each, for in here we only have one unit. Okay, so if we will just look at this node in here, and I want to calculate the error term at this node, so this is going to be the error term. I need to calculate delta 2, all right, at layer 2, because this one will be delta 1 at layer 2. And this one delta 1 at layer 3, and this is delta 1 at layer, delta 2 at layer 3. And this is, of course, delta 1 at 4, and we only have one unit. So see, the weights in here are coming from, these are the lengths, the outgoing lengths. Okay, and for those outgoing lengths, we have our thetas. So we have theta 1, 2 and theta 2, 2, and that's at layer 2. So you take the delta that we calculate in this layer, multiplied by this weight, plus this error term multiplied by this, and this is going to be our delta to 2. Okay. And how this was calculated? This was calculated from the delta term at this layer multiplied by the weight in this layer, and that's it. Okay, because it's only one outgoing link to this layer. So this is how the errors are propagated from the all the way from all the previous layers all the way to the internal layers. So so at each layer, there's a question in here. The number of features at each layer, are we reducing the number of features? Not necessarily. So you can have an intermediate layers with many nodes. All that we can say in the intermediate layers, we are creating new features. Okay. How good those features are pretty much is determined by how accurate at the end your method is, and by which you can try and reduce the number of nodes or increase them in the intermediate layers, and even the number of layers itself, because those are like hyperparameters that you need to tune. And the choice in here, where we're using a sigmoid function, which is a logistic function, to have a behavior similar to logistic regression for us to understand what's going on. And still, sigmoid is one choice that we still make. But remember, there are also other kinds of activation functions that we can choose. Okay, so once we have performed our forward propagation to calculate the activations, and then we calculated the deltas at each layer, except of course the input layer. We don't have that. We don't have error associated with the input. And remember this, we need to do this for all of our training samples one by one. So you start with the first training sample, you go forward phase, calculate A's, backward phase, calculate the deltas, and this is a way by which we accumulate the deltas. And remember in here, at each node, we have a delta term, and we have also an A term, an activation term. So this capital or this delta, the triangle that we're using in here, set this to 0 for all of the nodes. Okay, so we will calculate, in addition to A and this small delta, we will have a big delta that we will use as an accumulation for all of the training. So, the A's and the small deltas for each training sample. But then when we go over all the training sample, we keep the errors multiplied by the activations in each node as a way to accumulate for all of our training samples. And at the end, when we're done from all the training samples that we have, at the end, the capital deltas that we have in each node, we divide this by m, the total number of samples, and we keep this in a new parameter or a new variable. We call it d in here, I, j, l. So pretty much the loop in here, to go over all your training samples, you accumulate the deltas, which will record the activation multiplied by the small deltas that we have for each node. And when we're done from this loop, for all the training samples, we will end up with, in each node, we will end up with those accumulations of activations multiplied by deltas, by errors. We divide by m. And this is going to be our D, okay? Now, we need this for the gradient descent or any optimization algorithm to work. And this value that we accumulated in here will be our this notation in here. J of theta is our cost function. I will explain that in the next slide. And this notation in here that you see in this part, this is a derivative or a partial derivative term. Okay, so at the end, this value that we calculated in each node is our partial derivative of the cost function at theta. Okay. Now, of course, there is a math behind how did we get there, like how, and that's why like we needed to do those calculations in each node is for us to, at the end, to be able to calculate the partial derivative of the cost function at theta. Okay, because this partial derivative later on in the optimization algorithm that we will be using, gradient descent, will tell us how to update thetas to minimize this cost function. So the partial derivative in here, if you guys are familiar or if you remember calculus, and for those who didn't take calculus, I will explain it, and I have a slide to explain why do we need this partial derivative, or what's the purpose of this partial derivative to our estimate of those thetas. Again, we have initial values for theta, random initialization, but then again, the errors that we calculated will be used to know how much we need and to what direction our changes of those theta will lead us, by which at the end we will have a minimum cost. And the cost function in here, you can think of the cost function simply as the error. Okay, like the cost function here is how we represent the error. So in logistic regression, and before going to logistic regression, in linear regression, we all remember the cost function in linear regression was basically the sum, the residual sum of square. That's the objective function, right? This is the function that we need to minimize. We need to minimize the error. So it was simply y minus h theta of x, if we assume h theta of x is our hypothesis, square. Okay, so the sum of the difference between the true, that's outcome, y, and the predicted outcome in here, h theta of x, square, and sum. So that's going to be the cost function. This is our cost function in linear regression, and our job was to minimize this function. So you need to choose thetas, you need to select parameters for thetas that will give us a minimum cost. Now in logistic regression, we have a different formulation of this cost function, and that's the function in here. Okay, so it's two terms, and our job in here is to minimize this cost function, and this minimization here corresponds to coming up with accurate prediction or accurate classification. Since our neural network is stacking multiple logistic units together, so we need those summations in here over. So this summation in here is over the samples. M in here, for your question, Tara, M is the total number of samples in your training data. The total number of samples in your training data. So that's, the cost in here for I equal 1 to m. You calculate yi log h theta of xi. So yi is the true outcome or the true class, and h theta x of I is the predicted class. So you do this for all and you divide by m. That's going to be the cost j of theta. Now for a neural network, you need to do that for all the units. Capital K is the units in here because neural network is a stack of multiple logistic units. So in gradient descent as an optimization algorithm, we need both. You need the cost function and you need the partial derivative of, or the derivative of this cost function at, and then you will need to evaluate at thetas. We understand why we need the cost function. This is, pretty much to tell us how big is how big is the error that we're making, or the errors that we're making, and we need the partial derivative to tell us the direction by which we can change theta to minimize the cost. So in calculus, for those of you who remember, we needed the partial derivatives in minimization algorithms or in optimization algorithm to lead us to the values by which the cost is minimized. So it will be, where to go. Should we add or should we subtract from theta? Okay, so just for the time being that we have, before answering all your questions, to explain gradient descent with just a simple example. If you have your cost function j of theta, and if you only using two parameters, okay, so let's assume we have a very simple model with only two thetas, and gradient descent in here is a way by which we find the values of theta where the cost is minimum. And if you look at this figure in here, this is the search space of the cost function. The cost function is minimized maybe at this point in here. So this is going to be corresponds to the values for theta 1 and theta 2, 0.8 and 0.4, where the cost is as minimum as possible, and maybe it's 0. And of course, if the cost function is 0, it means you have 100% accurate prediction. Your predicted classes are the same as the true classes. So since we initialize thetas randomly, and maybe the initialization will be somewhere in here. So maybe your initialization of theta 1 and theta 2 may be at the top of this little hill in here. That's the random initialization. So, and this is how much cost associated with this theta 1, theta 2. Now, gradient descent in here is gonna iteratively change the values of theta 1 and theta 2 to get to a point where the cost is minimized. Now, the partial derivative of this cost function is needed to tell us where to go from this hill in here. So from this top of the hill, gradient descent, the first application of the partial derivative will, tell us that, okay, maybe we should move a little bit to here. And now this is how much the cost. And then the second iteration, it will maybe lead us to this point, then it will go downward all the way, because it's an iterative algorithm. So it will get us all the way to the point where the cost is minimum. And at each step, we're changing the values of theta 1 and theta 2 with this direction. So that's what's happening in here in this phase. Is once we accumulate, we calculate the error terms at each node for all of our training data. We apply gradient descent to understand the direction of, if we update those thetas, the direction that will get us to the point where the cost is minimal. Okay. So M, the terminology in here, M is the number of training samples. I don't have N in here. I only have M as in Mary. Okay, we don't have N. Okay, so pretty much for all of the training data, for all of your training samples, you accumulate the activations multiplied by the error terms, and then you apply gradient descent to update theta. Okay. Now, this is going to be, we will be doing this on multiple phases. So neural network works, and again, this is gradient descent. One of the classical optimization algorithms. So you do this in multiple phases, and what I mean by that is, once you're done from all of your training data to kind of calculate those partial derivatives, you can do multiple phases. So you go over the training data again for a second phase, and you do the same thing. And we do that, n number of times. And this is like a parameter that you can also tune, that you can, the stopping criteria, how enough, how much, how many times you need to go through all of your data multiple times to be enough for your neural network to have a good accuracy. So that's the total number of iterations on all of the data. So that's going to be the stopping criteria. It's different than cross-validation. This is not cross-validation. All right. So I know, that there are like a lot of details for gradient descent, and we don't have, it's beyond the scope of our course. But if you need anything about it, I will share some slides as a reference for you if you want to understand more about gradient descent. Any questions? So the other thing is the slides are available for all of you. The code as well is available. We didn't have time to go through the code, but again, if you have any questions, you can send an email, and I can explain to you what's going on in the code as well. Questions? Okay, so again, I will upload the slides for a gradient descent, and again, it's not required. It's just for your reference if you want to understand gradient descent algorithm. Although nowadays we're using more sophisticated, more advanced optimization algorithms than gradient descent, and it doesn't have to be iterative. We have really good advanced optimization algorithms that can work on all of the data at once, vectorized optimization algorithms, and it's more efficient and faster, and guarantees that the function is minimized at the values that will be estimated for the parameters. All right, so that's it then for today. I will see you next time, and we can start with unsupervised learning. All right, guys, you stay safe and stay home, and see you next time.